Hi everyone. Just covering your feedback questions from today. Let's see here. What do cis and trans mean? So cis and trans are both derived from Latin. I had to look up the etymology of this. Cis means on this side of. So things being on the same side. Trans means across. Those are literally the translations from the Latin. Cis is on the same side. Latin means across from each other. So when you're dealing with cis-trans isomers, in the case of the example we were looking at today, in the cis isomer, the chlorines are on the same side of the double bond, quote unquote. They are both on the top half, supposedly, of the double bond. As opposed to in the trans configuration when they are on opposite sides of the double bond. So I hope people can kind of see that. And that's essentially all cis and trans mean, either on the same side or across from each other. And we've used those same terminology before for another example. We did this last week when we were talking about polar versus nonpolar molecules. This is an example for xenon dichloro-difluoride. Actually make sure these Lewis structures are correct. In this case, the fluorines are across from each other. They're on opposite sides. So this would be considered a trans isomer. And in here, the fluorines are on the same side of the molecule, so to speak. They are relatively close to each other. So this is sometimes called a cis isomer. And there are other examples of when things can be cis or trans, but they are both. You'll see other types of isomerisms probably when you get to organic chemistry, but they're all sort of based upon the idea of things either being on the same side or being on opposite sides. How do you do polar and nonpolar structures of NH3? So I think that question was sort of geared from how I was looking at, okay, C2H3. The other example I did today, where I asserted there wasn't a polar or a nonpolar form. Ammonia doesn't have polar or nonpolar forms. It only has one form. It doesn't have multiple isomers like these two molecules do. NH3 only has one particular molecular structure, and it happens to be a polar structure. The nitrogen is more polar than the chlorines, so it pulls nitrogen is more electronegative than the hydrogen, so it pulls the electrons towards itself in these bonds. And then you have electron density up here, so as a result, the entire molecule has a net negative partial charge on the top side of the molecule and a net positive charge on the bottom side of the molecule. So you actually can't do a nonpolar form or a nonpolar structure for ammonia. It's always going to be polar. How do you determine the exact bond angle, and how do they compare among different molecules with the same geometry? So in many cases, you can't predict the exact geometry, especially if you are dealing with molecules that have lone pairs in them. So I've got a few different examples up here on the top. CH4, that one has a tetrahedral geometry. If its electron group geometry matches its molecular geometry, if all the bonding, all the attachments in the Vesper theory, basically if you have known lone pairs, so this molecule, its Vesper formula is AX4. If it has known lone pairs, then you can say exactly that the bond angles are 109.5 degrees because it's tetrahedral. Can't spell tetrahedral there. And those are going to be 109.5. They're all going to be exactly equal to 109.5 degrees. That won't be the case for molecules like NH3 and H2O. Now, they have tetrahedral electron group geometries, because I have AX3, I'm sorry, actually, AX3 E for NH3 here. So it has 4 attachments, 4 electron groups around it. 3 of them are bonding pairs in the atoms, and one of them is a lone pair. So there are 4 groups around it. So it has also a tetrahedral electron group geometry. It has a trigonal pyramidal molecular geometry if you're just looking at the atoms, but if you also look at all of the electron groups, including the lone pair and the bonding pairs, then it has 4 electron groups around it, which gives it a tetrahedral electron group geometry. So you start by saying it should be 109.5 degrees. And then you use the other corollary to VSEPR theory, which is that lone pairs repel more than bonding pairs. So even though the idea is that each of these electron groups are all trying to get as far away from each other as possible, and they are repelling each other, and the optimum configuration for 4 things that are equally pushing on each other as much as possible, the optimum geometry gives you bond angles of 109.5. But in this configuration, the lone pairs pushes more than the bonding pairs. The lone pairs are just electrons. They take up a lot of space because they're trying to get far away from each other. The bonding pairs are somewhat compressed because they're being attracted towards nuclei. So they're a little bit smaller. They don't push out as much. The lone pair pushes out a lot. And because it's pushing out, it's basically pushing these guys down closer to each other. And so you get bond angles that are a little bit less than 109.5 degrees. In fact, the bond angles for NH3 are about 107 degrees. 107 degrees. I was going to say 107 degrees Celsius. Whatever. Anyway, 107 degrees. Again, so it's a little bit smaller, and it's because the lone pairs are pushing more than the bonding pairs. And the same thing happens for H2O. H2O has 2 lone pairs on it and 2 bonding pairs. So it would have an AX2E2 VSEPR formula. So it has a bent geometry, but its electron group geometry is the same as methane and ammonia, as CH4 and NH3. Because it has 4 attachments, 2 lone pairs and 2 bonding pairs. So they will have a tetrahedral electron group geometry, so I would expect these bond angles to be close to 109.5 degrees, but because these lone pairs are pushing on the bonding pairs, the bond angle ends up being less than 109.5, and it ends up being even less than in NH3. In H3, it's actually 107 degrees Celsius. In water, it's about 104. I keep saying Celsius, 104 degrees for water. And again, the bond angle is smaller than in ammonia because you have more lone pairs, and the lone pairs are pushing more than the bonding pairs. So that's how you can roughly predict bond angles. You start by figuring out the electron group geometry, so the basic geometry, if you want to check basically this first column here in our figures. That sets you up your base geometry, or what I like to call the electron group geometry. And then based upon those base angles, the bond angles get a little bit smaller as you substitute bonding pairs for lone pairs. And because the lone pairs push all of the other bonding pairs more. What causes sigma bonds to twist? So this was one of the questions I mentioned, or this was the last example I went through in class today. Why do bonds twist? For the same reason that anything moves in a molecule, which is that things are always moving. That's kind of one of the big ideas from quantum mechanics that I have a tendency to sort of glaze over, is that motion is random. And as a result, you can't predict where something's going, and you can't predict where it will be found. And in essence, that means that nothing stays still. If something stayed still, then you know exactly where it is, and that would violate the Heisenberg uncertainty principle. So everything is always moving in a molecule. The nuclei are moving, the electrons are moving, they're twisting, they're moving this way, they're moving that way, and so the molecule is always fluctuating a little bit. The nuclei are always trying to move around, and so they will sometimes naturally twist as part of their random motion. So it's just a natural random occurrence that will occur, unless there's something to prevent it. like in the case that we worked through today, if you have a pi bond there, to twist the molecule would require raising energy. You would need to break the bond and have an input of energy, and that energy would need to come from somewhere. So that just won't happen randomly. I mean, it can, but it's not energetically favorable random interaction, so it's less likely. There's a general relationship with things being of high energy cost, low probability, low energy cost, high probability that it will happen. And for twisting of single bonds, that doesn't require much of an input of energy because you don't have to break any bonds. So those are random motions that will happen relatively easily. So that's why sigma bonds will, it's not so much that bonds in general will twist just due to random motion. Your question is what causes sigma bonds to twist? Again, the question is why would a bond twist in general? And again, it's just due to random motion. Sigma bonds can twist because it doesn't require breaking the bond. It doesn't require a large input of energy. So if something doesn't have a cis or trans form, does that mean it can't be classified as nonpolar or polar? So short answer is no. Just because a molecule doesn't have cis or trans configurations doesn't mean that it can't be classified as polar or nonpolar. Yeah, commonly if you have cis and trans isomers, one of them is polar and one of them is nonpolar, but a molecule can be polar and not exhibit cis-trans isomerism. So let me give you an example. So I'll do the formaldehyde molecule, which we did today in class. And in this molecule has polar bonds. Carbon is more electronegative than hydrogen, so it pulls electrons towards itself, and then oxygen is more electronegative than carbon. So the electrons are pulled in this direction. So overall, the molecule has a net dipole. Electrons are generally pulled towards this end of the molecule, so you end up with a partial negative charge and a partial positive charge. And as a result, the molecule has a net dipole, so this molecule is polar. It doesn't have cis-trans isomerism. I can't switch around the hydrogen so that they're both, one of them is going to be, something could be over here. Let me finish up this Lewis structure. So I could have these two lone pairs here. I can't switch things to opposite sides of the double bond because it's symmetric around the double bond. So it doesn't have cis-trans isomerism at all. It doesn't exhibit that property, but it can still be polar. So yeah, to answer your question is if just because something doesn't have cis-trans isomerism doesn't mean that it can't also be polar or nonpolar. There's not immediately a correlation between those two. What is the conclusion from drawing all of these figures with the orbitals? What are we trying to find? We could be trying to find a lot of things. At this level, I mostly just want people to kind of get used to drawing these diagrams. Essentially, what we're trying to figure out is what are the types of bonds? Are they sigma bonds? Are they pi bonds? Once we know whether they're sigma or pi bonds, we also want to know what types of orbitals are overlapping to create them. That's kind of what I'm trying to teach right now. Now, the ramifications of that, there are lots of them. We looked at one today, which is that because of the way double bonds are formed, they are formed from sigma bonds between hybrid orbitals, and they also have pi bonds, which are connecting above and below. Because of how that double bond is formed, you don't have free rotation. Rotation would require breaking one of the bonds. The bond is rigid in some fashion. Let me see, I do have a molecule example of this. So this is kind of an example of a double bond. This shows you the bonding, the pi bond being above and below the bond. So I can't twist this. It's rigid, but it basically prevents me from doing it. But if I had something a little bit simpler, if I had something that had this type of geometry, so this also has a They both have the same trigonal planar geometry, but this one is constructed such that it has just like basically you're only going to have a sigma bond here, and sigma bonds can be twisted without breaking the bond. Now, in reality, this molecule doesn't just have the sigma bond, it also has, can I get this lined up? Kind of. It has both the sigma bond and the pi bond. So if there's just a sigma bond, the sigma bond can rotate. The pi bond can't rotate. So that is one of the things that we might be trying not so much to find, but explain. Things that we can now explain about a molecule given our understanding of how the bonds are formed. I had a few other examples that I was going to look into. I can discuss those perhaps either in a separate video or maybe on Friday's lecture. We'll see. But I don't want to make this video too long. So those were all the questions from today. I'm going to say one more thing. Later on in organic chemistry, you will start making judgments about how reactions occur, how molecules and atoms come together and actually make bonds or break bonds. And if you're talking about molecules coming together and making bonds, you need to understand how those bonds are made. One of the ways to conceptualize how bonds are made is from the viewpoint of valence bond theory, which is that bonds form through overlaps of orbitals. So you need to know how those orbitals are oriented. You need to know their geometry. You need to know how they overlap or don't overlap. You need to know what will prevent them from breaking or not breaking, their preferred geometry. All those things will go into have a bearing in terms of chemical reactivity, how molecules, bonds will break or not break or form or not form. So that is something that we're kind of laying the foundation for now, but we're not going to have an opportunity to go into too much detail in this course, but that you will get lots of that in your next year of chemistry, in organic chemistry, and to some extent also in inorganic chemistry, not so much in PChem. PChem will delve deeper into the fundamental nature of those bonds, but going further than that, going up to the breaking and formation of multiple bonds, that's not a topic that's normally covered in physical chemistry. It is covered in organic chemistry, which should be next in the series for you folks. So you will come back to this, I promise. Other than that, that's all the questions and feedback from today. I look forward to seeing everybody on Friday. Have a good day.